Hello, this is Manuel Garcia, and this is lesson 17.5, General Plane Motion. And the objectives of today's lecture are to analyze the planar kinetics of a rigid body undergoing general plane motion, like the yo-yo that we have in this illustration. So yo-yo is this little toy that is we always played when we were kids, and you just throw it up and down, so it is translating up and down, and at the same time is continuously rotating. Or if you are doing some of the tricks that you put the rope and the yo-yo follows the trajectory, so it's also translating while it's rotating. Well, besides these fun applications, we have some multiple applications. A more serious application would be, for example, the soil compactor. So the soil compactor that is moving forward. So it's moving forward with some velocity and probably with some acceleration. And the forces of the traction are pushing the front roller, and the shaft in the roller, it's supporting some loads. At the same time, you have some bearings here that are supporting some loads, and you would like to know what are the magnitudes of those loads that probably are different if you consider the static situation or the dynamic situation when it's moving. So if we analyzed the front roller, so we can draw a free body diagram and a kinetic diagram. So these are equal. So in the free body diagram, we can analyze the forces. So the forces that we have, for example, are the forces in the support in the shaft. So we can have a px and a py. So let me put the two forces. So there's a force px that is pushing the wheel, the roller forward, and we have another one that is supporting the weight. So this is py. So of course we have the weight, and the wheel is in contact with the ground. So we have a normal force, and there is a friction. So because we are moving to the left, so the friction is opposed to the movement. So the friction force F is at the point of contact, and is actually the one that is responsible for the rotational movement, because if there is no friction, it will slip. So on the kinetic diagram, we can see that the only possible acceleration of the center of mass G is to the left, or if it's stopping to the right, but it's just horizontal. So we have an acceleration in the center of mass G. So this green one is the center of mass. So the magnitude of the kinetic element is mass times acceleration of G plus the kinetic moment, which is Ig multiplied by alpha. When a rigid body is subject to external forces and coupled moments, it can undergo both translational motion and rotational motion. So this combination is called the general plane motion. So let's consider our body, and we have the free body diagram in which we can include the forces F1, F2, and F3, and it can have some moments. So M1, M2, let's draw it in the different direction, and we can also identify the center of mass G in both the free body diagram and in the kinetic diagram. So the sum of the forces and the sum of the moments have their equivalent in the kinetic diagram. So we have the mass times the acceleration of the center of mass, and we have the moment of inertia with respect to G multiplied by alpha. So if we write the equations of motion, We can either do it in the xy coordinate system. So we have the sum of the forces in x equal to mass multiplied by the acceleration of the center of mass in the x direction. The sum of the forces in y equal to the mass multiplied by the acceleration of the center of mass in the y direction. And we have the sum of the moments around g, which is equal to the moment of inertia multiplied by the angular acceleration. Or if we write it in the tangential normal coordinate system, so we have the sum of the forces in the normal direction equals to the mass multiplied by the acceleration of the center of mass in the normal direction. The sum of the forces in the tangential direction equal to the mass multiplied by the acceleration of the center of mass in the tangential direction. If we take the moment with respect to a different point, let's put the point P, then the sum of the moments with respect to that point is equal to the moment of inertia with respect to the point multiplied by alpha plus the mass time acceleration of the center of mass multiplied by d, and d is the distance, the perpendicular distance of the line of action of the mass times acceleration vector with respect to p. When we analyze the rolling motion of wheels or cylinders or disc, we may not know if the body rolls without slipping or if it slips as it rolls. So if we have if we draw the free body diagram and the kinetic diagram, we can identify the different forces. So for example, we can identify the weight that is applied on the center of mass, and if we are pulling it with a force P from the center of mass, so that's a horizontal force. We also have a normal force at the contact with the ground, and if this is moving to the right, we have a friction force on the left that we don't know the nature of the friction force, if it's static or if it's kinetic. On the right hand side in the kinetic diagram, we have the mass times acceleration term, and we have the moment of inertia multiplied by alpha. So we can set up the equations of motion in x. We have that the forces that we have are P and F, the friction force, and this should be equal to the mass times acceleration of the center of mass. On the y direction, we have the weight W, or mass times gravity, and it's going down, and up we have the normal force. So the normal force minus mass times gravity is equal to 0 because we don't have acceleration in y as it's moving just on the surface horizontally. And our sum of moments with respect to the center of mass is equal to the moment of inertia multiplied by alpha. So the moments are the moments of this force, so we are taking moments with respect to g. So the moment of this force is a force is making this rotate in this direction, so it's a negative moment. So let me put the negative moment multiplied by r, and r, let me draw it in a different color here, is this radius r. I'm going to delete it to avoid confusion, that only we need to put in the free body diagram forces. So distances are necessary for the momentums, right? Now, this is equal to the moment of inertia on the right hand side, the moment of inertia multiplied by alpha. So what are the unknowns of this problem? So we probably know the force P that we are applying to our wheel. We don't know the friction for sure. Um, the normal force, well, we can get it from this equation, but let's count as an unknown at the moment. So we can do the countability of unknowns and equations. The acceleration of the center of mass, AG, is another unknown. And finally, what else do we have? Alpha. So how many unknowns do we have? So we have 1, 2, 3, 4 unknowns. So we have 4 unknowns and 3 equations. So we are in trouble. We cannot solve this problem unless we include an additional equation. The fourth equation can be obtained from the slip or non-slip condition of the disk. Now let's remember a little bit about the friction factor. So assume that we have a block and we are applying a force F, and it's initially static, and so we start to increase the force. So there is a friction force that goes in the opposite direction. That friction force is a function of the normal function multiplied by the coefficient of friction, and that coefficient of friction increases as the force increases until the maximum point Fs, when the body start to move, so we start to have slipping, and at that point we have that the friction force is equal to the static coefficient multiplied by the normal. And after that value, so we keep increasing the force, then the friction force remains constant at a value of mu k multiplied by the normal, and mu k is the kinetic coefficient of friction. Now, the procedure to solve in this situation is that we can just assume that there is no slipping, so we have rolling, so this is rolling, and use the acceleration of the center of gravity equal to alpha multiplied by the radius. So this acceleration at this point is the corresponding to no slipping. Do not use the friction factor equal to the static coefficient multiplied by the normal, because we could be in any of these situations. So this is at the maximum point before slipping. After solving, you need to verify the assumption that the friction force is less than this value, because that means that we are in this range, so this is valid. On the other hand, so we can't assume slipping, so we can assume that the friction force is equal to mu k multiplied by the normal, so we are in the slipping region. And the fourth equation, for the fourth equation, and in this case we cannot assume that the acceleration of the center of mass is equal to alpha multiplied by r. This is an example of how we can approach the problems involving rotation and translation. So in this example we have a spool, and the spool has a mass of 200 kilograms and a radius of gyration of 0.3 meters, and the coefficient of kinetic friction between the spool and the ground is 0.1. So they are already telling us kinetic friction, so it must be slipping. And we need to find the angular acceleration of the spool, and notice that the acceleration in this is in this direction, so what's the meaning of that? And the tension in the cable. Okay, if the acceleration is in this sense, that means that there must be like a motor here that is making this move in this direction, because we have a cable here, and this cable will be under tension when we start to move here, and it will produce a slipping, and the cable start to wrap around the spool. Now, if we draw the free body diagram of the spool, so we have a force that is in A, so point A is located over here, and we have a force, that's the tension, to the right. Let me draw, this is G, the center of mass, and we can put the force due to the weight in G. We have the normal force, and we have a friction. So what is the direction of the friction? So this is moving towards that direction, so friction factor always oppose, so friction factor has to be to the left. So this is the friction factor, and the normal, the friction force. And the kinetic diagram, we have our center of mass G. The acceleration has to be just in the x direction, so this is mass multiplied by the acceleration of the center of gravity, and we have the moment of inertia multiplied by alpha, and alpha is in the counterclockwise, so Ig multiplied by alpha. Now, the first thing that we should notice is where is the instantaneous center of zero velocity, so the IC for this case, because in a normal wheel that is non-slipping, the instantaneous center of zero velocity is located in between the wheel and the surface, but there is a slipping here, so this is not zero velocity. But if we look to this point A at that distance has zero velocity, because this is acting like the ground, so it is rolling on the cable. So the IC is located in that point, so the IC is located at A. So the acceleration of the center of gravity of mass is equal to r multiplied by alpha. So where r, I'm going to draw r in green, is a vector that goes from the instantaneous center to G. So the acceleration of G is equal to 0.4, which is the distance from G to the point A, multiplied by alpha. So let's write the equations of motion for this situation. From the free body diagram, we have that the sum of the forces in X is equal to mass multiplied by the acceleration of G, and we can rewrite this equation. The forces that we have are, the horizontal forces are F and T, so this is T minus F equal to mass multiplied by the acceleration of G, and the acceleration of G is equal to 0.4 alpha, so this is equal to mass multiplied by 0.4 alpha. Now the sum of the forces in Y equal to mass multiplied by the acceleration of G in the Y direction, which is 0. So in the Y direction, we have, in the vertical direction, we have W and the normal force, the weight and the normal force. So we have the normal force minus the weight is equal to 0, and so from here we can conclude that the normal force is equal to the weight, and the weight is the mass, which is 200 kilograms, multiplied by the gravity, which is 9.81. So this is equal to 1962 newtons. Now we still don't know the values for alpha and the friction force. So from our first equation, let me rewrite the first equation. This equation 1 here, we have that T minus F equal to the mass, 0.4 multiplied by the mass multiplied by alpha, and the mass is 100. Now the friction force, because it's slipping, so we know that it's equal to the coefficient of kinetic friction multiplied by the normal. So T minus mu k multiplied by the normal equal to 0.4 multiplied by the mass, and the mass is 200 multiplied by alpha. So let's keep replacing. So we have that T minus the coefficient, which is 0.1 multiplied by the normal force, which is 1962 newtons, and plus 0.4 multiplied by 200 multiplied by alpha. So this last equation, after multiplying, we have that T is equal to 196.2 plus 80 alpha. So this is one equation, but the unknowns that we have are alpha and T. So we need a second equation. We still have the sum of the moments at G. So we have the sum of the moments at G equal to the moment of inertia at G multiplied by alpha. So what are the moments that we have at G? At G we have the moment of T and we have the moment of F. The other forces are passing through the center of mass. So for T we have T multiplied by this distance, which is 0.4, and the moment is the moment is R cross T. So it's negative, and this moment is also negative because it will make this to rotate in that direction. So let's write the moments. So we have minus T multiplied by 0.4 minus F multiplied by 0.6. They are at a different distance, and this is equal to the mass multiplied by the moment of inertia. Well, the moment of inertia, which is the mass multiplied by the radius of gyration square and multiplied by alpha. So from this equation we know everything except alpha and T. So we have two equations. We have equation 1, and equation 2. Solving these two equations, so solving for T and alpha from 1 and 2, we have that alpha is equal to 750 radians per second, and T equal to 797 newtons.